Hello, I'm Justin Hamlin, an undergraduate student currently researching at the Michigan State University College of Engineering under Dr. Caroline Chapansky. And so today I'm going to be discussing the dispersions of nanoparticles in organic solvent with a focus on Hansen solubility parameters. So more specifically, I'm going to explain the process of how we can determine the solubility sphere of a specific nanoparticle through dispersion testing. So what exactly are Hansen solubility parameters? Well, put quite simply, it is a quantitative system created by Hansen that can predict the miscibility of two or more species. So this system breaks the cohesive energy density into three parts, dispersive, polar, and H-bond forces. And we can see the derivation of those three numbers in the two equations below. So once we determine the HSP values of a particular species, we list those values in coordinate form, and that tells us the specific dispersive, polar, and H-bond values respectively for that species. Now, these values can only be determined experimentally through solubility tests, which I will discuss more in detail later. However, once these HSP values are known, they can be compared to other species in order to predict the miscibility between two species. So as a general rule of thumb, species with similar HSP values are miscible, whereas species with largely different HSP values are immiscible. So that brings up the question of how do we know which HSP values are similar enough to be miscible and which HSP values are so largely different that they are immiscible? To answer this question, Hansen presented a sphere model plotted in HSP space to represent the entire solubility of a species. So in this model, the Ra value of a solvent gives the distance in HSP space between that solvent and the species in question. And we can see the equation to determine that Ra value in the equation below. The Ro value gives the radius of the sphere of that species. The relative energy distance, or RED, is defined as Ra divided by Ro. And in an optimal HSP model, all bad solvents will lay outside of the sphere, and consequently will have a RED greater than 1, and all good solvents will lay inside of the sphere with a RED less than 1. This sphere model allows a distinct line to be drawn in which species on one side are soluble and species on the other side are insoluble. So now I'm going to talk about the methodology of the system and how we can actually determine the HSP sphere of a species through experimental observation. So for the materials of this lab, we have taken cellulose nanocrystals, or CNCs, as a model nanoparticle for HSP investigation. However, other nanoparticles can be used in place of our species, and the methodology will likely be identical. You will also need Matlab and Excel and various pure solvents. Now, when you are selecting solvents for this experiment, you want to use solvents that encompass a wide range of HSP values. For example, you want a range of solvents of high dispersive values and low dispersive values, high polar and low polar, high H bond and low H bond. As a reference, the solvents listed here encompass a relatively wide range of HSP values. And to find the HSP values of common solvents, we use the Hansen Solubility Parameters User's Handbook. For the dispersibility tests, this is where we determine which solvents are good and which solvents are bad for the species in question. Because our cellulose nanocrystal came in slurry form, we had to take the water content of the slurry into account when the nanocrystals were added to each solvent. However, the end goal is to make a 1 weight % solution of nanoparticles. So 0.1 grams dry CNC was added to enough solvent to make the total weight of the nanoparticle and the solvent 10 grams. This mixture was then stirred vigorously for 30 seconds and then sonicated for 30 seconds. This process was repeated for each solvent. Then these samples sat undisturbed until the sedimentation time had passed for that solvent. The sedimentation time corresponds to the duration of time over which a species will form a precipitate and bad solvent. And we can see the equation to get the T-sed value below. I have also listed the solvent sedimentation times for this particular study to the right. So you should note that the sedimentation time will change depending on the nanoparticle density and solvent properties. Once the sedimentation time for each solvent had passed, all dispersions were placed in front of text and observed. A ranking of 2, corresponding to good solvents, was given to dispersions in which the text could be read well. A ranking of 1 for partial solvents was given to dispersions that were uniformly turbid and the text could not be read well. A ranking of 0 for bad solvents exhibited visible separation or precipitate. Now, after giving each solvent a solubility ranking corresponding to the nanoparticle in question, these values were placed in an Excel sheet along with the name and HSP values of the corresponding solvent or solvent mixture. Again, the HSP values were determined using the second edition Hansen Solubility Parameter User's Handbook by Charles M. Hansen. Now, once a rough sphere is determined for a species, solvent mixtures are often used to test the limits of the sphere and squeeze the solvent into an optimal radius. If the solvent mixtures were used, the combined HSP value for the mixture was determined as the sum of the products of the dispersive values and the mass ratio. This equation also applies to the polar and H bond values. Similarly, due to the water incorporated into the CNC slurries, this created solvent mixtures of water and solvent. So using the equation above, the mass ratio of H2O was determined to be 0.2464, and the equation on the bottom was used to calculate the normalized dispersive, polar, and H bond values for this slurry and solvent mixture. So here's a picture of what our data looks like in the Excel spreadsheet. On the left, we have the name of the solvent, followed by the pure solvent HSP values right here. And on the right side, we have the grade for that solvent and the mixed solubility or the normalized HSP values. So these values in the middle, they don't really apply to what we're doing right now, and also these values right here. So for ease of use, this large table was narrowed down to just include the solvent name, the normalized HSP values, and the solubility rankings. And so this makes it much easier to move this data into the Matlab algorithm, especially just because you don't have random solvents in between these that you didn't actually use and that don't have rankings. It's just easier to highlight an entire one section and then move it into Matlab. So next, we will take this Excel data and plug it into a Matlab algorithm in order to calculate an HSP sphere for the nanoparticle in question. So in the case of CNCs, partial solvents were considered good because these partial solvents fit into the calculated sphere quite well, as with other good solvents. However, in some cases, you may want to ignore partial solvents and simply not include it in your Matlab calculation. It all depends on your preferences and how largely these different rankings affect the sphere. For this study, we used a slightly altered version of the Garagese algorithm. In short, this algorithm is designed to create a HSP sphere with all bad solvents outside and all good solvents inside. When I initially used this algorithm, it took hours to get an output if the data fit or the goodness of the sphere was less than 1. So I altered it to make this output much quicker. So here is a flowchart that represents the Garagese algorithm. So first, right here, the algorithm takes a guess value. And so the first guess value is the average of all the HSP values entered into the algorithm, and that is its starting point. So next it undergoes an optimization function, this whole section, to maximize the data fit of the sphere, or again, the goodness of the fit of the sphere. And this function keeps repeating multiple times, altering both the radius and the center point of the sphere, and it follows the following pattern. If the RA of the solvent is greater than 1, or if the red is greater than 1, then the solubility value for that solvent should be equal to 0. If the solvent is 0, a value of 1 is outputted, and if the solubility value is not 0, then a penalty value is created of e to the power of the difference of the RA and RO values. Similarly, if the RA is less than 1, or the red is less than 1, then the solubility should be equal to 1. If the solubility, or if the solvent is good and equal to 1, then no penalty is taken. However, if this is not true, then the same penalty is taken as e to the power of the difference between the RA and RO values. At the end, a data fit value is calculated, which is the product of all penalty values to the power of 1 divided by the number of solvents. If no penalties are taken, then a data fit of 1 is outputted. However, if penalties for that run do exist, then the data fit will be less than 1. The algorithm will repeat the process thousands of times while slightly altering the HSP and RO values for the sphere. And out of all of the runs, the run with the data fit closest to 1 is taken as the output, and the HSP and RO values for that run are displayed. So these are just kind of the steps that I usually follow when I am using the Matlab algorithm. So first I will open the solvent database matrix, delete about half of the current data in the matrix, just in case my new data has a few less solvents. And then I copy and paste the new data over that old data. And then type in save solvent database data, and that just allows the solvent database to be able to be used in the algorithm itself. So now that the solvent data is saved onto Matlab, there are two optimization functions to choose from. One is HSP.m, and that's from the Garaghese algorithm, and that's the default HSP optimization. And so it does not have any bounds, and so that should be taken into account. That some data sets with a data fit less than 1 have very strange outputs, spheres with radii of like 1,000 or so, or negative numbers, which you don't really want. And so I slightly altered it to create a different algorithm, which is called bound.m. And so this algorithm has bounds so that the solubility sphere is not large or negative. And it's also much quicker than HSP.m. So in most cases, these two values are the same. However, I often do run both functions and use my judgment to choose between the two if there are any slight differences. So this is the Matlab algorithm. So I'm just going to explain it to you real quick. So this whole area right here is basically just the first guess area where it takes the mean of all of the entered values, delta D, delta P, delta H, and it just uses that as its first guess value. And then here, this is the optimization function. So here it actually uses a for function. Originally it used a while function, but that took a very long time if the data fit was less than 1. And so I changed that to a for, and it seems to speed up the process quite a bit. So in this function, it calls upon this QF function. And so what this does, I already explained it, but if RA is greater than RO and the solubility is equal to 0, then it outputs 1. However, if in this case it is the solubility is equal to 1, then it gives a penalty. And if RA is less than RO and the solubility is equal to 0, then it gives a penalty. And if it is equal to 1 or 2, then it gives a 1. And so this here gives the output data fit value. And so this whole function keeps repeating and repeating until the data fit value is the maximum data fit value is found. And then that value and the corresponding center points in RO are listed here at the end as delta D, delta P, delta H. And so now I'll just explain how I actually go through it. So first I double click the solvent database, and then that pulls up this data area. And so normally I would delete about half of this data, just highlight it and then go to delete row. However, I'm not going to do that right now just because I don't want to put new data in there. So after I do that, I will type save solvent database data and click enter, and that just saves it into the folder and allows the algorithm to actually use that. And then what I'll do, I'll run the HSP algorithm first. And so it takes about a minute to complete this time. And so I will actually just pause the video and I'll come back to you when a result is close. All right, so here we got our answer using the HSP algorithm. So this is the data fit, 0.95, and here are the delta D, delta P, delta H values along with RO. And these are measured in the square root of megapascals, or megapascals to the power of 1/2. And so up here we can actually see the different HSP values, their solubility, and their corresponding relative energy distance. So because the data fit is less than 1, we know that there must be some discrepancy in the data. And we can actually find that right here. There is a solubility ranking that is equal to 1, and the red is greater than 1. So this is a partial solvent, so it is going to be weird. Partial solvents are kind of an interesting topic just because there is some dispute as to whether they should just be ignored, considered as one, or there have been other systems created just to account for these partial solvents. But because partial solvents were considered good, and because the red is greater than 1, that causes the data fit to be slightly less than 1, which that explains why that happens. And so now I also have my bound algorithm here. And so the only difference is right here. I just use a different optimization function. So if you want to use that instead of the HSP function, you can. I have found that they come up with relatively similar results, except the bound has bounds, obviously, just in case there's some weird stuff going on with the HSP function. If you get really large numbers or negative numbers, I find it's much better to use bound. And also one more advantage, bound is a lot more quicker. It comes up in like 2 seconds, and it's also very similar numbers, 0.95, 18, 16, 15, and 9.6. I think it's almost exactly the same as the HSP algorithm. And again, here, this is the discrepancy, solubility ranking of 1 and a red of 1.0005. All right, so finally, graphing the spheres is also a very important part of showing results to the public. So for this study, we used Origin Pro to graph the spheres, and I will show you how to do that right now. So pull up your Origin Pro. This is just a brand new file. Click File, New, Function Plot, and 3D Parametric Function Plot. And so I already have a HSP sphere template kind of saved, but really what you have to do, I have 4 variables, R, X, Y, Z. X corresponds to dispersive, Y corresponds to polar, and Z corresponds to H bond. So what I do, just do an R coefficient in front of each variable, and then add X, Y, and Z in front of the other variables, accounting for polar or dispersive, polar, and H bond. So let's say we have a radius of 9.7, X of 10, Y of 15, and Z of 8. Okay, so then we click OK, and it comes up with this sphere and this matrix, and you don't really have to do anything with this matrix. It's just kind of there. Hide. Okay, and so sometimes you might actually find that this sphere instead looks something like an integral shape like this. And so all you have to do is double click this, go to surface, parametric for surface, matrix 2 is X, and Y matrix is matrix 3. Click apply, and then you have this nice sphere here. And also you can edit the function of the sphere at any time. I find this really helpful. If you run the numbers again and you find that the radius is actually 12, you can just change that number, click apply, and it makes it bigger. So one thing that I find helpful when I'm graphing other data, such as good solvents and bad solvents and partial solvents alongside it, I like to get rid of the mesh and create a transparent fill. Put it up to 80. And so what that does is it makes it kind of transparent, so you can actually you can see other points inside of it. And so if there are other good solvents inside the sphere, the outside of the sphere doesn't actually block the entire points inside, but you can actually see inside of it, kind of like you see here. Now, one note when using this graphing software is that sometimes bad solvents with a red very close to 1 that closely border the edge of the sphere will appear inside of your sphere. So you can see it right here, this little red square. This is actually inside of the sphere on this graph. And so this is simply because of that coefficient of 4 in the RA equation that we saw before. So in reality, due to directional forces, the solubility sphere of most species should really be represented as a solubility epsiloid, where it's kind of longer in one end and thinner in another. However, for simplicity, we can just address these irregularities in our studies, if any appear, and we can safely ignore them. So that concludes my presentation. I hope you enjoyed, and now you can go on and calculate and graph these solubility spheres for yourself. So thank you for watching.